begin part B, or the second part of our Earth and Space science. And here we go. We have a diagram here of the Earth's cross-section. Cross-section means they've cut it like in half, perhaps, and you can see the core, then the mantle, and then they have all these little arrows. Scientists believe that forces in the Earth's mantle moves Earth's crustal plates. We talked about earlier how those plates separated, and they're actually floating on the Earth's outer core there, not outer core, excuse me, out on the mantle. The arrows in the diagram then represent convection currents, which are currents that are carrying heat. It can't be ocean currents because it's in the Earth there. It's not gravity. Gravity always goes straight down toward the center, and it's not wind because it's inside the Earth. But that's where we have that's molten there, and so that does move. And convection moves through liquids or gases, fluids basically. So those are convection currents that they're showing you there. The White Cliffs of Dover are made of a white sedimentary stone called chalk, which was formed when shells and skeletons of small marine organisms were deposited in a thick layer. An examination of the Cliffs of Dover from top to bottom. So remember, we always mentioned this in one of the problems from part A, that if you're on the top and here's the bottom, naturally the oldest things are on the bottom as long as the rocks haven't been disturbed. And on the top would be your younger rock layers, which includes your younger fossils. Older things would have to be on the bottom because they just keep getting covered up. So from top to bottom would be younger to older fossils. Younger to older fossils. Number 30, an oceanographer is traveling from the west toward the east on the Atlantic Ocean. She collects rock samples from the seafloor every 5 kilometers. The oceanographer stops and determines that the rock samples are getting progressively younger as she moves toward the east. What conclusion is best supported by this data? Well, if they're getting younger, then she's probably getting higher. And that's what happens if she's traveling toward a mid-ocean ridge. Let me show you a picture. We have another problem that has a mid-ocean ridge on it. So here's another picture of that. The oldest stuff would be on the bottom. So if she's getting younger, then she's traveling toward that mid-ocean ridge. And this happened to be the one in the mid-Atlantic. So that would be A. In the 1600s, Danish scientist Nicholas Steno studied the relative positions of sedimentary rocks. That means who's higher up, who's lower, etc., etc. He determined that sedimentary rocks typically form layer on top of layer. So if undisturbed, the bottom layer is the oldest. Today, this idea is known as the law of superposition. So really, they gave it a big name. But this is kind of a theme again that we see on the OGT. The oldest rocks are on the bottom. Youngest rocks are on top. That is if it's been undisturbed, of course. This law is a way to estimate relative ages. So you don't know exact age, but you say, oh, this rock layer is younger than this rock layer because it's on the top. How could the law of superposition be applied correctly to this cross-section? It says the youngest sedimentary layer was deposited by glaciers. And I don't think we have to look anymore because look at the legend. The glacial deposits are on the top. So that again is the youngest. Okay. And ooh, this is bad. The youngest sedimentary layer can be found at the very bottom. The youngest is on top because they just keep depositing themselves on top of each other. And here we go. There's the picture of the Mid-Atlantic Ridge cross-section. And this is again how I like to say the Hawaiian Islands are being formed. A magma can come up between things, and if it gets up high enough, then it creates like another island, etc. Which area is likely the oldest crust? Again, the oldest would be toward the bottom, which is number 1. Oldest on the bottom, youngest on the top. Now here is an example of disturbed rocks. So if they had been undisturbed, you can see the distinct layers. Now here they've been disturbed a little bit. So this is, well, let's see, let's read it. An earth science teacher places 4 pieces of carpet padding representing sedimentary rocks between 2 large bookends as shown. She then pushes the bookends toward each other, and what geologic process has the teacher demonstrated? This would be called folding, because there hasn't been any actual break in the rock layers. There hasn't been a break in the rock layers. So this would be like a fault here if you have an actual break. But that's just folding. They're getting crunched together. Okay. Here's another cross-section of an area of Earth's crust. There's a heat source, non-permeable rock, which means you can't get through it. Here's permeable rock, which you can go through that. And there's some fracturing, though, of course, and more non-permeable rock. In which area of the diagram is a geyser most likely to form? The geyser is that hot steam that comes up, that shoots up after being heated, maybe from the mantle. And so, of course, the geyser is going to go up through this area here where we have the permeable rock. That would be most likely in C. And you may have heard of Old Faithful, that geyser at, I think it's Yellowstone National Park. The cross-section below shows the orientation of rock layers in a given area. Notice how they're not going straight anymore. So it said, what geologic event most likely caused the folding and faulting? So they're telling you that you're looking at folding and faulting. And the geologic event that causes that is the tectonic activity. That's the plates. Sometimes it's called plate tectonics. So when the plates are knocking against each other, things can happen. Like there has to be a fault because there's not enough room, or maybe the folding. So that would be an example of the plate tectonics. In some areas, magma chambers exist close to Earth's surface. We saw a picture of that in this other question. Water seeping into the ground becomes heated by the rock overlying these magma chambers. What is most likely to occur when the heated water under pressure rises back toward the surface through fractured rock? That would be your geyser formation. And here's what they're talking about. They're heating the water. There's your heat source. Okay, so that's a geyser. Geologists installed tilt meters in a tectonically active area. So the plates are moving around a lot. Tilt meters can detect very small changes in the slope or the tilt of Earth's surface. These changes result from the upward movement of magma beneath the Earth's surface. What event could be predicted by monitoring these changes? So the tilt is from the magma beneath Earth's surface. So this kind of ties in with a potential volcanic eruption. Just like they asked where the next volcano was going to be formed in the Hawaiian Islands. And that was because they were being formed from the magma. So that would be give you a potential volcanic eruption. On number 21, the graph below shows the seismic wave velocities at various steps within the Earth. So seismic waves can help you locate your earthquakes, etc. So this is marking the beginning of the Earth's liquid outer core. So you're going from solid to liquid, which makes a big difference in how the waves travel. So the big difference is seen right here. See how where you're dropping? Waves are here, then dropping. So area C would mark that boundary, that difference in seismic activity waves. James Hutton is often referred to as the father of modern geology. His detailed observations and theories about Earth processes opposed the accepted theories of his time. One of his contributions was the development of what he called the Great Geological Cycle. He theorized that most rocks were igneous in origin. The igneous rocks could then change into sedimentary or metamorphic rocks. The chart below shows locations of several rock types and the minerals they contain. What evidence from the chart could be used to support Hutton's theory that most rocks are igneous in origin? So if you take a look, here's different locations, different rock types, the sedimentary, igneous, metamorphic, and we have rock names, but check out the minerals. Here's muscovite in the sedimentary, we have muscovite in the igneous, we have muscovite in the metamorphic, and again in this sedimentary in North America. We have quartz, 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 quartz. We have biotite mica, biotite mica, biotite mica, biotite mica. So I would think that the evidence in this chart would be that the rocks are made up of many of the same minerals. So that would support the fact that maybe they were all igneous to start with, and then they formed either sedimentary or metamorphic as well. In Aristotle's treatise on meteorology, he stated that the same parts of the earth are not always moist or dry, but they change accordingly as rivers come into existence and dry up. And so the relation of land to sea changes too, and a place does not always remain land or sea throughout all time. But where there was dry land, there comes to be sea, and where there is now sea, there one day comes to be dry land. Aristotle was referring to the cyclic nature, cycles in the nature of Earth's processes. So things do tend to cycle around. What type of energy from the oceans is responsible for weather patterns? The oceans. The oceans are liquid, and we have thermal convection currents in the oceans. So the energy there would be thermal, and it would be also from convection currents. Okay. Number 13, most geologists accept radiometric dating techniques as valid because. So radiometric, so that's kind of, that root word is related then to radiation. Okay, so you may have heard of carbon-14 dating from radioactive substances. So the reason they accept these as valid is because of A, radioactive elements decay at a constant and measurable rate. So they're able to measure the amount of radioactive material left in an object, which can tell them how old that object may have been. And here it says all of them used for dating purposes have the same decay rate. No, different radioactive elements decay at different rates. Elements may have both radioactive and non-radioactive isotopes, but that doesn't explain why we're accepting them as radiometric dating techniques. And non-radioactive isotopes do not decay at the same rate. So A is our best choice there. Here's a table about using radiation, radioactive isotopes to do dating. But this, be careful, because if you read this, you say, what's 1.25 by? You've look down here at your little legend. B, it's very small. BY stands for billions of years, and MY stands for millions. So they have this for different elements. And their half-life, how long it takes for half of it to decay. So if it takes billions of years for it to decay, you can't measure something that's not very old. So you have to use something like carbon-14, for example, is the radioisotope with the smallest half-life. It only takes 5,730 years, not millions or billions of years. So which isotope from Table A is the only one with applications for dating Holocene materials? So notice, Holocene materials are in this area from 0 up to about 10,000, I guess it says. So 5,000 can go into 10,000 about twice, but millions are way too big. That would be trying to measure, that would be like trying to measure the diameter of a certain tube that you might need by using a mile and saying what kind of mile that might be. So we would have to use carbon-14 because the Holocene epoch there doesn't span very many years. Now, like if you look at this whole Philistine epoch, it's huge because it goes from 0 to 2 millions of years, but it still doesn't go to any billions. So again, part of this is reading tables as well as knowing a little bit of background. Now we're going to talk a little bit more about outer space. Many scientists hypothesize that a cloud of interstellar dust, gas, and ice collapsed to form a nebula from which our sun and planets formed. What factor is responsible for causing most of this interstellar material to condense, forming our sun? That would be gravitational attraction. Gravitational attraction, then, is mostly responsible for that formation of our planets and suns. Which property of a star can be determined most directly from just its color? So from its color, you have an idea of its surface temperature range. Like our sun's kind of yellow, the red giants get cooler, there's some of the white stars are very hot. So the surface temperature can kind of tell by looking at the color. An astronomer investigating a star determines that the light wavelengths she observes are longer than those expected to be emitted by the star. So the light wavelengths she sees are longer than expected. What can be concluded about the motion of the star relative to the Earth's position? This is called, you may have heard this, is called that redshift. Redshift is to light like the Doppler effect is to sound. For example, when the ambulance is coming towards you, you hear a different pitch than when the ambulance is going past you. So that's the same kind of idea here. So the redshift tells us that the star is moving away from us. And they use this redshift to talk about the universe still expanding. And you have probably seen that maybe if you've ever looked Big Bang, the introduction to that TV show. So the universe is still expanding. And so pretty much things are going to be moving away from Earth. When examining the redshift of galaxies outside our own, every galaxy appears to be moving away from the observer. This observation supports the Big Bang because it indicates that the universe is still expanding. So that's what that redshift says. Still expanding. Here again, it's just basically reading a chart. It says, according to some theories, Earth's sun is approximately 5 billion years old. After about 10 billion years, this type of star runs out of fuel. The hydrogen in the core becomes depleted and cannot be fused to form helium. The graph below illustrates the chemical changes that occur inside a star at specific times. So the question is, use the information. What is the hydrogen-helium content inside a star, the approximate age of our sun? Well, our sun is approximately 5 billion. So here's at birth, after 5 billion, after 10 billion. So we should be using chart 2 to talk about our sun. So notice in the core, we have quite a bit of helium in the core. Okay, so this just says distance from the center. So this is toward the center of the sun. This is on the outside. So let's read our possibilities. The hydrogen content decreases as it reaches the outer edge of the star. The hydrogen is the one in non-shaded, and the helium is shaded. So the hydrogen content actually is lower here and higher here. So that is backwards. The helium content is higher at the outer position than it is in the core. No, the shaded area helium is more toward the core. So that's backwards. The hydrogen content is higher at the center of the star and then decreases toward the edge. And that's pretty much what it said in A, which is kind of backwards. How about D? The helium content is greatest at the center and then decreases toward the outer edge. So here it is. It's greater toward the center, and then see this big blob turns into a lot smaller there. So that would be D. And that's our last question on Earth and Space, Part B. Please make sure you're studying for your OGT. Look for more videos, say on maybe environmental science and life science. Good luck. Bye for now.